Okay, Bismillahirrahmanirrahim. Assalamualaikum dan salam sejahtera semua. Good morning, good evening, good afternoon, or good night, depending wherever you are, whenever you are watching this recorded video. So today's topic I'll be discussing on a phasor diagram of synchronous generators circuit model. So previously we have seen some few examples, some soft examples on how to calculate different parameters. For example, we want to calculate the voltage, the generated EMF voltage, given all of the parameters, the current and the terminal voltage and different power factor. Okay, and you can see that at different power factor, we can see that the voltage behave differently. For example, for lagging power factor, we can see that the generated voltage induced EMF is larger than the phase voltage, and for leading power factor that the EMF voltage is smaller than the phase voltage. So we're going to continue on analyzing again this circuit, but we're going to take a look at it into two different way. So again, so far we have only been given the equivalent circuit model based on this circuit equivalent formula. Okay, the voltage relationship between the EMF voltage and the voltage of the terminal and the current and okay, so basically this is the relationship. So we can use that whenever to find the parameters. This is basically the KVL equation across this loop. Okay, so however, now we are going to discuss a bit further on how to analyze the circuit model and understand the operation and the behavior of the voltage and current at different power factor. And we are going to use in terms, we're going to analyze that in terms of what we call a phasor diagrams. Okay, all right, this is just a little bit basic on a phasor diagram. So because the voltages, the current are all in phasor, so you can see that all this symbol here, the arrow here, represent phasor, meaning that all this magnitude, these parameters, the current and voltage, basically they have magnitude and angle. Okay, so they are usually expressed as vector. Remember vector here, there's a complex plane here, so you can represent a vector. There's a starting point and then there's an end point. Okay, so the length of the vector represents the magnitude and the angle here represent the phase angle. Okay, and you can project them into whether the real or imaginary part depending on the angle of the plane. Okay, so as I said just now, you have to analyze them on the complex plane. Complex plane means you have a real and imaginary part of each vector. Okay, this is what we call a phasor diagram. And basically, I want all of you to remember how to do phasor operations. For example, multiplication or addition, subtraction, division, and inverse. All this basically you have learned this in your previous class. So make sure you remember how to manipulate, to use these basic formulations in order to solve for the parameters. Okay, so yeah, it's some review. Okay, so also a brief review that, okay, just to review that if you have a lagging power factor, then the voltage will be lagging. Basically, it's if you take the rotation is in that way and the counterclockwise rotation of the phasor, then if you have a current lagging falling behind the voltage, is so-called lagging power factor. And if you have the current and voltage are in phase, meaning that both of them are in the same direction, then you have a unity power factor. And if you have a current out of phase but in front of, if leading the current, so you can see that I leads the voltage in that direction. Okay, then you have a leading power factor. Okay, and then let's review a little bit on what you call a power triangle, if you guys remember. So basically, a power triangle is a complex plane which describe the apparent power S in terms of the real power. This is real power, and the imaginary power, I call it sometimes a reactive power, Q. Okay, this is a real power, and this is the unit is in var, and the real power unit is watt. Okay, you have to remember that this is basically the real power watt. that the utility charge and make profit out of it. Okay, so this is very important to maintain this P, and also it's very important to also to maintain the Q, but the Q is not it's not normally bring any profit to the utility company. So it is something a power that is required, but it is not really bring any money to the charge to the customer utility. So you can basically, if you have a apparent power, okay, if you have, let's say, the apparent power is S, the unit is VA, okay, and let's say here, and S equal P plus JQ, okay, of course, if you can split them into real and imaginary power. And let's say if you have a positive Q, okay, let's say the phasor is in this part of the plane, and then you have a theta here, and you have a positive Q, and then of course the P is always positive, okay, if you want to maintain the real power, okay. So the Q can change. I can say that the Q can either be on the positive side, on the negative side. So if you have a positive Q, and basically you have a lagging power factor, and it means that the reactive power is being delivered, is being sent out, okay. But if you have a negative power, a negative Q, then it means that the reactive power is being absorbed, okay. This is something that you have learned previously, and I hope you still remember this operation lah. And then of course you have to remember also that, okay, let me clear this thing up, okay, because this the apparent power, basically if you have let's say the same power, you can have a greater value of apparent power, but you can also have with greater what you call Q, okay. So you have let's say S4 here, then of course it's the same power, same lagging power factor, but the power is still delivering the same real power, but now you have a more reactive power, okay. So, and then this reactive power also is proportional to the current that the generator has to deliver. So as you can see, that's why a more lagging power factor is not really that desirable. The most desirable is unity power factor, is the best one, because you don't have to export any Q, because Q doesn't bring any profit, right? So if it's better for the utility to have as close as possible, as small as possible, close to unity, but if you have sometimes when it happens more than, let's say 0.6 or 0.7, then the generator have to work harder to supply more current, but the utility is only getting profit for the same power, okay. So lagging power factor is not so good, and leading power factor also not so good. So the best is to keep it as close as possible. Mostly lagging power factor is the one which is more common in most utility system, but lagging power factor is basically very less common, okay. All right, so this is just a brief review on lagging, on the different type of power factor, and also a power factor triangle. Okay, so let's talk about I think about what's the phasor diagram looks like for a unity power factor. Okay, so I think we have discussed it before in our previous lecture, but I'm going to just go through very quickly. Okay, so in this case, the key here is we basically want to maintain the same when you have a unity power factor, basically you have a current and voltage vector in the same direction or in phase. Okay, and after that you have this voltage drop across this resistance here. Okay, now you take a look at this circuit here. Okay, you have a voltage drop across this resistance here. This is IARA. The current multiplied by resistor, you got a voltage, and then after that you have the voltage drop across the inductor, and then you combine all the three voltages together, you'll get the voltage, the total voltage generated. Okay, so basically okay, now the operation is that, okay, this V phase here is basically the voltage that we are going to serve the load with. Okay, and it is very important for utility to maintain this voltage as close as possible to the rated value. Okay, because this is basically the load that's supposed to get this voltage, and if you put a different voltage, then the load might not operate in proper function. Okay, so assuming that this is our objective here, we want to get the same voltage. Okay, want to maintain the same. This is a phase voltage. Yeah, phase voltage here. Okay, all right. So for unity power factor, as you can see that we assume the same phase voltage. Okay, the induced voltage EA will increase slightly. As you can see that, okay, the E is a little bit greater than the phase voltage. All right. So that is the phenomena for unity power factor. E will be always greater than V phase, but not that much difference lah. Okay. So in order to maintain the voltage, EA need to increase. Okay, so because let's say you have a unity power factor, the current here increase, and the voltage EA need to increase. But how to increase that? Take a look at this formula here. So to increase E maximum, the generated induced voltage, we can only increase the flux, because this is need to be maintained. Yeah, the frequency to be maintained, and this is a constant number. So this flux here, the air gap flux depend on the amount of field current. So if you want to increase the flux, you need to increase the field current. Okay. Okay, so this is what I call a normal excitation. So a very slight increase in E, but not that much. So it's a normal excitation. Okay, so as you can see also, so at unity power factor, the generator will only deliver real power, because you can see that there's no imaginary power here. So I mean the S is equal to, because V and I is in unity, so S multiplied by VI is always a real value lah. Okay. So how about lagging power factor? Okay, lagging power factor, if you can see that the condition is that you have a current lags the voltage by a certain degree, and this degree is what we call a power factor degree. Okay. And then after that, you have a voltage drop across this resistor, and you add up to the voltage drop across the inductor, the synchronous reactance here. Okay. And then after that, you add all the three voltages together, you get the internal generated voltage. Okay. So what can we learn from this situation here? So basically, we also always want to maintain the V phase here, but in order to maintain a constant V phase, you can see that the generated voltage here will increase significantly lower than EA. We have seen that in the previous example. Okay. So I also forgot to introduce you that there's the delta here, the power angle. The power angle is the angle between E and V. Okay, E and V. All right. Okay, so to increase the voltage, generated induced voltage, we can only increase the flux. Okay, by increasing the field current. All right. So again, the same explanation down here, and this whole situation is called over excitation. Means that the over means that the voltage here, the EA is also known as excitation voltage. So excitation voltage is higher than the phase voltage. So it's because over excitation. So I think that's where the name come from lah. So also that from lagging power factor, the generator will deliver both P and Q. Okay. Because we'll see about that on one formula. Why is it we deliver positive Q? Okay, so generator acts as like a capacitor to supply the reactive power to the load. Okay, and finally we have seen this before. Okay, I just repeat very briefly. For leading power factor, you have a current lead the voltage by a certain degree. Okay, and you want to find a phasor relationship between all the voltages. EA, this voltage across the screen resistor, and the voltage across the resistor, and the phase voltage. So when you plot the voltage, and then you have a voltage drop across the synchronous reactance is this way. Okay. Okay, I have explained that before. And then when we combine them together, then you have a generator voltage is this generator. Okay, this phasor here. So what does it mean? That you can also conclude that always for leading power factor, okay, for leading power factor, always remember that the voltage E, induced voltage E, or EA is the same thing, will decrease significantly lower than the phase voltage. So always remember that EA will be lower than the phase voltage. Okay. Or you can say that the phase voltage will be higher than the EA voltage. It doesn't matter, it's the same thing lah. Or V phase will be higher than EA. Okay, depending how you look at it lah. So okay. So and then you can reduce EA. To reduce EA, okay, we refer this equation using this calculation here, right? Okay, sorry. And the only way you can reduce EA is by reducing the flux, by reducing the field current. Okay. And then this situation is called under excitation. Okay. All right. So basically, what we can explain here is that at leading power factor, basically the load which has a more leading, more capacitance will try to push the voltage at the terminal, at the phase voltage here, much higher than the EA. Okay, that's what does it mean. Similarly, if you go back earlier, previous slide, okay, so for a lagging power factor, you can see that EA is greater than V phase, meaning that if you have a lagging power factor, the V phase will be reduced, to lower than the generator voltage. This is what happened, because the load here, basically what affecting the phase voltage here is that this current here, right? This current here will be lagging, and because of that, the voltage across this phase here will reduce, will go lower, okay, because of the lagging load, and then it will be much lower than the EA. All right, so that. Okay, so okay, this is another example that I think we have seen this before, and I've shown you how to do the calculation here. You can go through and yourself, and I just add this slide here. Okay, so we can do some observation. Let's do some comparison on the three different type of power factor, and what happened to all the parameters. Okay, so the key things here, basically you want to have the phase voltage to be as constant as possible. Okay, this is your desired value. So in any situation, whether a unity, lagging or leading power factor, that is your objective. Okay, because that is the purpose of having a generator. You want to produce two things. Basically, you want to have the same frequency at the bus, and then you want to have the same voltage at the bus. Okay, so voltage and frequency, this is the two parameter that always that utility need to provide for a certain value. Okay, for example, in Malaysia, the system must be maintained at 50 Hz, no matter what, no matter how many generators are there, no matter how much power is being delivered or absorbed, the frequency must be fixed. Okay, similarly with voltage. And then we can see that for unity, for different power factor, for the induced voltage will be a bit less than V for unity, and it will be higher. I wouldn't say it's increased. I would say it's okay, increase higher. And for leading power factor, it's reduced. Okay, and the air gap flux, because you are reducing the generator voltage E, of course, it will be proportionally depend on the air gap flux, which also depend on the field current. So you can see that these two parameters here, air gap flux and field current, basically will have the same response. If the field current increase, the air flux will also will increase. Okay, because let's say the formula is like this: if you increase the field current, the flux will also increase, and the generator voltage will also increase. That is the relationship here. Okay, if you lower the generator voltage, and then the field current and the flux will reduce. Okay, this is the different type of excitation. If it's a unity power factor, you call it normal excitation. If it's lagging power factor, we know it as over excitation, and leading power factor, we call it under excitation. Okay, as I mentioned before, the synchronous speed of the generator and the frequency will always be constant no matter what. Okay, and lastly, the power flow. So for unity power flow, generator will only deliver only the real power. But for lagging, generator will deliver real power as well as deliver the reactive power. Okay, and then for leading power factor, the generator will deliver both P and deliver Q. Okay. Okay, so as you can see that it's not very desirable to have a lagging and leading power factor, but we cannot avoid that because the system is predominantly dominated by these two, either leading or lagging. Very very rare you have a unity power factor in a large power system like in Malaysia. The power factor you can see mostly around lagging around zero point 0.9, perhaps to maybe zero point 0.9 something. Okay, it's around the zero point 0.9. So okay, so okay, we're gonna stop right now. We're gonna continue at the next slide. Thank you very much in the presentation.